Think we're going. Hey everybody, welcome to the Hangout. We're doing the Space Out today. It's DNews plus NASA JPL. And I'm Trace Dominguez. I'm the host from discoverynews.com. With me here is Ian O'Neill. Ian, why don't you introduce yourself?
Hi Trace, I'm Ian O'Neill. I'm the space producer for discoverynews.com, and I'm very excited to be here.
We've also got Don and Amy. Why don't you guys introduce yourselves too?
Hi, I'm Amy Mainzer from JPL, asteroid scientist.
I'm Don Yeomans, manager of NASA's Near Earth Object Program Office at JPL.
And Brian?
Hi, I'm Brian Muirhead. I'm the chief engineer of JPL, and I'm leading NASA's asteroid redirect study.
So today we're going to talk about asteroids and near-Earth objects, in case you didn't get it from all the experts that we've got here with us today. Feel free to tweet at us or go into our Google Hangout Q&A area if you have any questions. You can use the hashtag #SpaceOut on Twitter. But let's get started. So what does your JPL office do? What's the Office of Near-Earth Objects, Don?
Well, basically, we take the data that's provided by NASA-supported telescopes, mostly in the U.S. Southwest, and we take that data, we fit orbits to these objects that are recently discovered and the ones that have been discovered previously. We run their motions out for 100 years on the computer and see if any of them make an interesting close Earth approach. And if they do, then we do impact probabilities and get the word out to the observers to watch the objects on our short list.
Cool. So what are we doing? What are we doing about these near-Earth asteroids, you guys?
Well,
who wants to jump in on that one?
The first thing we have to do is find them, of course, and find them early enough so that any of them represent a problem or a threat to Earth, we could do something about it. And that's we're also studying techniques for mitigation or deflecting any of these objects that might be on an Earth-threatening trajectory.
Wow. Okay. And sounds pretty amazing. What other missions and stuff are we using? Like, is it like people that are working for NASA and JPL? Is it amateur astronomers? Who's looking for these things?
Well, this is a pretty broad community that searches for these objects, and it really is a global effort to find and track them. And it's even got a space-based component as well at present. So we rely extensively on professional astronomers. Like Don said, a lot of them are in the Southwest, and they're actually kind of modest-sized telescopes. You'd think that you would have really giant telescopes looking for these things, but by and large, most of the telescopes are kind of slightly larger than your cable pop. They're really not that big. And there's a few kind of major surveys using these sort of modest-sized telescopes, and then they're supported with a very big network of people all around the world, amateur astronomers and professionals alike, who help chase after these.
And also, Amy, you've got a very, very special mission you look after. Tell us a little bit about NEOWISE and why it's so cool.
Yeah, so this is our first space-based survey for asteroids that's really done this in a systematic way, I would say, to try to go out and hunt down these objects using a space infrared telescope platform. And this was a little telescope that wasn't actually originally designed to go hunting for asteroids, but it turned out to be pretty good at it, so we kind of took it over. And now we use it full-time for looking for asteroids.
And probably the cool thing about that mission was, because I actually met Amy literally 2 days ago. She was speaking at the ISDC in LA, and she was speaking on my track that I was heading. And I was amazed, actually, by how small this mission is. I was expecting like something the size of a Hubble Space Telescope that would be used for this important mission. But actually, it's about the size of a tabletop. I mean, why is it that these infrared telescopes are so tiny in comparison to, like, say, the optical telescopes? I mean, is that really a difference in the optics, or is it something more fundamental with the infrared observatories?
Right. I mean, so asteroids kind of emit light in a couple different ways, or they reflect sunlight. So the sun hits them and bounces off their surface, and then you basically, with visible light, you're seeing that reflected sunlight. But the sunlight also warms up the asteroids, and they re-emit that energy at infrared wavelengths. So it's basically heat. So with an infrared telescope, you're actually sensing the heat coming off of the asteroid, not the reflected sunlight bouncing off of its surface. And because of that, because these are heat-sensing detectors that we're using with NEOWISE, we need to be away from the Earth. The Earth is hot. And of course, the things we're looking for are, kind of nice little warm room temperature asteroids in space. So we need to get away from the warm Earth. But the consequence of that is if you have an infrared telescope that's kept cold because it's away from the Earth a little bit, off the surface, it becomes very, very powerful. And in fact, the 40-centimeter NEOWISE telescope is equivalent to thousands of telescopes that are much larger on the ground operating at the same wavelength. So it's very beneficial for infrared studies because you're looking for heat to try to get away from the warm Earth. And that really helps us find the asteroids.
That is pretty cool. Do we have like I mean, how long have you guys? Yeah, literally. Nice. Please be as punny as you like. We enjoy puns. Over there. How long have you guys been doing this? Is this a new project? This is been around a while?
Well, this particular telescope was originally launched as the Wide Field Infrared Survey Explorer, or WISE, and we love acronyms at NASA. So WISE, it actually launched in late 2009, and it did a survey for 1 year in 2010 and the very beginning of 2011, and then it was put into hibernation. Originally, this was a telescope that was, like I said, designed for something completely different, for astrophysics. It was actually designed to look for ultra-cool stars and very bright galaxies at infrared wavelengths, but it turned out it was a pretty effective tool for looking.
Uh-oh, we seem to have had a halt there.
We've got a glitch.
Well, we'll move on and hope they come back to us here.
Yeah. We'll get back to
Brian, I was going to say, Brian, you've been awfully quiet over there.
Well, my job's to chase down the asteroids that Amy and Don find, and ideally, ultimately, to bring either a whole small asteroid or a piece of a large asteroid back and put it into orbit around the moon, that then visit with humans.
You want to grab an asteroid?
Absolutely. Sounds pretty crazy, doesn't it? That's right. We talk about lassoing an asteroid. So, yeah.
Well, how do you go about doing something like that? How do you pick an asteroid to grab? I guess first.
Well, that's Don, and that's kind of Don and Amy and all the people with their telescopes that are looking for asteroids. We're looking for relatively small ones, actually quite small ones, things in the 10-meter size or smaller. And those are hard to find, and we need ones that are coming close by the Earth. I think Don would tell you that asteroids of that size hit the Earth about every decade. So, and of course, the Chelyabinsk that hit not too long ago. So anyway, once they've identified an asteroid coming in with our ground-based telescopes, we want to characterize it. We want to try to use our radar, for example, to understand its size, improve its trajectory, and then if its conditions are just right, if it's coming in at the right speed, it's the right size, we will look at it as a possibility to go out and rendezvous with and come back and come back with it, I should say, in the early 2020s when we can plan on a human mission using the Orion spacecraft.
Yeah, one thing I've found, I mean, with like the survey missions that are searching for these asteroids, and especially the size of the ones you're going to be looking for to actually send a human mission to these, on a robotic mission to these asteroids. What's the main technical challenges from an engineering standpoint you facing? Because these things are moving fast, and it's one thing that they are coming near the Earth, but is there a certain velocity you're looking for? Because I couldn't imagine catching up to one of these things.
Well, yeah, there's actually some interesting issues associated with the velocity, but what we want is something that'll be coming back in the time period that we're interested in the 2020s. We are using a technology called solar electric propulsion, and using that we can go out and rendezvous with one of these bodies that are basically in orbit around the sun, coming back, flying in basically a near-Earth asteroid, near-Earth orbit, crossing near the Earth and near the Moon. And so once we've rendezvoused with it, our job is to then grab it. And we right now have a technology. We use a bag that is basically deployed with inflatables. We fly our spacecraft and basically dock with the asteroid, and then close the bag around it. Now you may ask, why a bag? Well, the reason is we don't know much about the composition of asteroids. We don't know how they're held together. We believe most of them are rubble piles. And so what we've done is come up with a solution of grabbing one that kind of doesn't care whether it's a rubble pile or not. If it's a solid rock, we could do something different. So once we got it in the bag, now these things are massive. This could be 1,000 tons of asteroid. So we can't really do much to change its velocity, except do it just enough so that we can nudge it on its trajectory such that it'll fly by the moon, and then we'll use the moon's gravity to slingshot it into an orbit around the moon. That's a stable. That will be a stable orbit that we can send crew to in the early 2020s.
That's cool. I've got Amy and Don back.
Hey.
Thank you. I'm glad you guys came back. It'd be hard to cover this without you.
Welcome back. We were just discussing capturing an asteroid, but we might want to step back just a minute and be like, how do we even pick an asteroid? How do you pick which one you want to grab?
Well, you have to find one of the right size so that the bag or the apparatus can pick it up. You have to find one that's pretty well observed, hopefully pretty well characterized in terms of its physical characteristics, its size, its rotation rate, perhaps a little bit of information about its possible composition. So we've got a fairly extensive observing program underway to look for these small ones. We found a couple that are suitable targets. We're looking for more, and the trick is, because they're so small and because we can only find them when they get pretty close to the Earth, we have to find them with optical telescopes, immediately get the radar on them, the two planetary radars, one in Arecibo, Puerto Rico, one in Goldstone in Mojave Desert. So we have to have radar, and then ideally we would also get near-infrared data from the IRTF telescope in Hawaii. So if we can get all of those observations within the first couple days of discovery, then we can put that object on our short list for possible targets.
Very cool. It's a process for sure. And you were saying you're looking for the smaller ones. So what about the big ones? That's Don. That's the one I'm worried about. It's the bigger one.
That's the one that keeps us up at night.
Yeah.
Well, we're talking about finding a target for the ARM mission, but if you're talking about finding ones that are on Earth-threatening trajectories, then we're looking actually preferentially for the larger ones because they can do so much more damage. A kilometer and larger object could cause global problems, but fortunately there's only about 1,000 of those, and we've already found 95% of them, and none of them represent a threat. On the other hand, when you get to smaller and smaller objects, you get more and more of them. So when you get down to objects that are the Chelyabinsk size, just 20 meters, but still capable of doing ground damage, then you've got millions of them, and we found less than 1% of that population.
So we still have a lot of work to do.
Yeah, it sounds like.
Yeah.
We've got a question in our Q&A section from Joshua Keel, who wants to know, how big does a meteorite have to be to make it through the Earth's atmosphere without burning up? That's pretty relevant right now.
Well, okay, so an object that's less than, say, 100 meters or so probably would not punch through the Earth's atmosphere and hit, but it could cause a substantial air blast and do ground damage. Anything larger than 100 meters or so would punch through and cause a crater, more than likely, and also create a lot of ground damage. So about 100 meters is the dividing line.
And that seems pretty good size.
It is pretty good size,
Yeah.
but our atmosphere is very effective in protecting us. So every day you should be thankful that our atmosphere is there protecting us from these rocks and, of course, providing us with oxygen.
Yeah.
Yeah, so
Now,
they're kind of like the Chelyabinsk kind of meteors that hit the atmosphere. What's their composition? I mean, are these like the rubble piles we were talking about, or are they something a little bit more solid? And say if something is, other asteroids that are made just of pure iron, I mean, will these things just come straight through the atmosphere as if it isn't even there? Or is this like a developing field that we don't really fully understand their composition?
Well, you put your finger on it. There are a wide diversity of asteroids. You go anywhere from ex-cometary fluff balls that you could break apart with your bare hands to rubble piles, a lot of those, to shattered rocks, solid rocks, and slabs of solid iron. So there's a very wide spectrum of asteroid types and compositions.
And that's why we want to gather as much data as we can about what they're made out of, how can we figure these things out remotely without actually having to spend a lot of money going to them. So, of course, observers on the ground use spectrographs to try to get, fingerprints, essentially, of the minerals that make up the objects. And then we can get some information also, too, when we look at their infrared signatures as well, because we can tell something about their reflectivity. So the darker objects tend to be more along the lines of the crumbly stuff that Don alluded to, whereas the brighter ones could either be stony or the dreaded metallic. We basically want to try to encompass as wide a range of capturing those characteristics as we can, and we use a lot of different techniques for that.
Well, that's what kind of techniques? I was just about to ask. I'm glad you brought that.
Well, one of the nice things we have is we have a wonderful collection of samples, meteorites. And so those are the bits and pieces that actually do make it all the way to the ground, and that's how we know so much about the compositional diversity of these things. It's not just what we see far away in space; it's also the little bits that we get to pick up. Chelyabinsk was a really wonderful example of that because it delivered so many pieces that can be analyzed so that we can see the diversity even within that one single object when it broke apart, what its internal structure looks like, how fragile it might be, how strong it might be. And what you would plan for mitigation strategies would depend greatly on the composition. So we know that broadly speaking, there's kind of three types. There's the carbonaceous types, the more crumbly stuffs that might be dead comets, some of them, that have burned up all of their ices. There's the stony types, which are like Chelyabinsk, the rockier bodies, and then a small percentage are metallic, but that's not the majority of them by any means.
Yeah, the holy grail of asteroid science is really to link meteorite types and their compositions with asteroids that are seen in space. So if we can take broadband spectra of asteroids in space and say that type is identical to the meteorites that we have in our museums and have studied over the years, then we can make the link that, well, that asteroid is almost certainly silicate rock or carbonaceous materials. So that's the goal, is to identify asteroids in space using these meteorites that we have on the ground.
So we'll be comparing what we know now and what we've found on the ground with, hopefully, something maybe in 2020, like Brian was saying. It's something we can grab as well, ideally. And then also, those are the two kind of legs we have to stand on?
Well, there's kind of a neat example recently from the Dawn mission. Dawn has just recently left the asteroid Vesta, which is a really big asteroid. But Vesta is thought to be the parent body of a particular class of meteorites that we see on the ground that have fairly unusual spectral signatures. They look kind of different than all the other ones, I'd say. And one of the great things about the Dawn mission is they were basically able to say, yep, these ones, that came from that one right here. And the explosion that chipped these guys off probably happened, X billion years ago. So that's pretty neat. I think there's a lot that's being learned now, even, that's really informing our understanding of where these things really come from.
Well, one thing I just have to ask, Don and Amy, where are you based right now? What is going on behind you? Because I get so distracted by these wonderful animations.
There's so much cool stuff.
Yeah, this is cool. I wish I had a big computer screen behind my head.
That's the you're seeing an animation of the Goldstone antenna, which is used not only to communicate with spacecraft, but it's also used occasionally to send radar beams out to asteroids, and so we can time how long it takes for the signal to get from the Goldstone dish that you see in the background to the asteroid and back, and knowing the speed of light, we can determine the precise distance of the asteroid at any given time to about the 4-meter level, which is really quite extraordinary.
That's really good. And what kind of distance is that with the Goldstone? How far away can it see something that size?
Well, it depends on the size of the asteroid, of course, but several million miles, tens of millions of miles, actually, depending on how large the object is and how slowly it's rotating.
It's one of those things where, with radar, because you have to send the beam out and then you have to get it back, it actually, it's a little harder to do than, say, for example, if you're just getting signals coming right off of the asteroid. So radar works at closer range. You get beautiful, beautiful data. It shows you the shapes, and you can even see boulders on surfaces. You can see craters. It's wonderful. But the objects have to get closer because you've got to both send the beam out and then wait for it to come back. So we learn different things from different techniques, and each one has a little bit of a different range. It's like having a toolbox. Some tools are good for certain circumstances, and others for different ones.
Got you.
But they all work together. It's kind of a fun example. With NEOWISE, we recently discovered an asteroid that's about, we think, around 300 or so meters across, and it's going to come within about 3 lunar distances in early June. And we know it's absolutely, there's no collision threat whatsoever, but it's a wonderful gold mine of science for us because the radar folks are going to pick it up, probably with Goldstone right here. And then we'll get nice shape data that we can hopefully combine with our infrared measurements to say something about what the material is like on the surface. And there's really no other way to do that short of actually going to these objects. So it all works together really nicely.
Cool. Yeah, it's a nice collaborative community. You've got the near-infrared folks that Amy works with. You've got the radar folks. You've got the optical observers. You've got a small army of amateur astronomers who are actually watching the light from these objects as it varies as the asteroid rotates, so they can determine rotation rates. So you've got the amateurs, you've got the professionals, you've got the infrared folks, you've got the radar folks, and they all work very closely together. It's a nice system.
Cool. That's a lot of people on there.
Mm-hmm.
And you said earlier the amateur astronomers as well. We had a viewer, Michael Fry, ask if we have enough eyes watching.
We would always like to have more eyes watching. And NASA has been looking at ways to expand capability for surveying for these objects. We definitely rely on observers all around the world because, when we find these things, of course, they're moving, right? I mean, it isn't like traditional astronomy where you're looking at a star that's, more or less going to stay in the same place. You pretty much know where that galaxy is going to be every day. But with an asteroid, the name of the game is when we first find these things, all we have are just a few snapshots of where it is, and you have to project forward in time to figure out where it's going to go. So the reason we need so many people watching is because as we accumulate more observations over longer and longer time, we get better information about the orbit. And it takes time to do that. So, and then, of course, the things have the wonderful habit of showing up when there's bad weather in some parts of the sky, or they'll show up in the northern hemisphere and then move to the southern hemisphere where a northern telescope can't look. It really is a global effort. And, of course, for our telescope in space, we find stuff all times of the day and night. Doesn't really care about the weather, certainly doesn't care about holidays or monsoon season in the southwest or southern hemisphere. So yeah, we really rely on a global network to help us out.
Yeah, sounds like it. We do get a lot of questions too, and I just want to tackle this while we're on the topic. Why, like in terms of Earth-killing asteroids, but in general, why are we spending money looking for this? So many people comment whenever we talk about asteroids about, couldn't we be spending this money on world hunger or something? And I find it such a kind of sad question because I feel like there's not really much of an answer that we haven't already covered. It seems like there are so many reasons to keep an eye out. Do you maybe want to respond to that? We get a lot of viewers who ask.
Well, we should be spending money on solving world hunger, but we should also be spending a small amount of insurance money on protecting Earth from a catastrophic collision. An asteroid impact is one of the few events that could take us all out like that. And so it's worth the modest amounts of money that NASA is spending to find these objects well in advance of a potential impact. These are very low probability events, but they're extremely high consequence events. So if we can spend the money, find them early, track them, and make sure that none of them have our name on it, we'll be doing the entire civilization on Earth a big favor.
Absolutely. That's very cool.
I just have a quick question. I mean, this isn't related to Earth hitting asteroids, but this is like relating to the upcoming asteroid rendezvous mission that NASA's planning. I was just wondering if Brian had any insight to which asteroids perhaps NASA's identified as possible targets for these missions?
Yes, we've got 2 targets right now that we consider valid targets. You able to hear me, Ain? Okay.
Yeah.
We've got 2 targets that we consider valid. 2009 BD and just recently 2011 MD has been put into that class. Both 2009 BD will be returning to Earth around June of 2023, and 2011, I think, August of 2024. So both of those look like valid candidates that we could go out and grab those asteroids. They're probably in the 5 to 6 meter class. I would like to point out, though, there's another option that we're looking at, and it's a very interesting one, in which we would go to a much larger asteroid like Itokawa or Bennu, which OSIRIS-REx is going to, and bring back a boulder from the surface of an asteroid. And the exciting part of that is maybe going to a C-type asteroid and bringing back a boulder from one of those. So that's our pick up a boulder option, along with the bag an asteroid option. So both of those are being evaluated right now, and by hopefully, there you go, there's the pick up a boulder picture. That option, along with the bag and asteroid option, are in study right now. We're evaluating both of those, and by the end of the year, we hope to make a decision as which mission we want to go fly.
Very cool. You said C-type asteroid. What can you give us an idea of what a C-type is?
Well, I'll let our asteroid scientists talk about that.
You want to take this one?
All right. Well, a C-type asteroid are dark, like the ones that Amy was talking about, that are very apparent in the infrared. But they also have some of them anyway, have hydrated minerals and even water ices. So that these are the objects that in the future may well be used to extract water, break the water down into hydrogen and oxygen, which is rocket fuel. So at some point, these asteroids could be resources in the inner solar system, sort of the watering holes and fueling stations for interplanetary travel.
Wow.
Well, that's well and good, but I want to know where the asteroids are with the titanium in them, the gold, the silver, all the important metals.
Yeah.
Well, these asteroid mining companies are talking about. I want to know where those are first. Okay, so if you can work.
All about the bling, yeah. All about the bling.
Well, there are asteroids that are rich in platinum group elements, much richer than those same elements on the Earth's surface. So, at some point, when we run out of these minerals and metals on the Earth's surface, or they become extremely scarce, it might make commercial sense to go out and mine these platinum group elements and bring them back, but not for quite a while. I couldn't develop a business case for that right now, but in the future, possibly that would make sense.
Right now we're trying to focus on finding them.
Yeah.
Before they find out.
That's important. You got to know where they are before you can go.
That's right.
Yeah. How do we know when we found, like you said earlier, that there are millions of these and we've only found a few % of them? How would we know when we found them all? Is it just we've mapped this part of the sky, or is there more to it?
Right. That's one of the things we work on with NEOWISE. During our prime mission, we used our infrared data to collect what we would consider a representative sample. In other words, equally sensitive to the bright ones and the dark ones, and we surveyed the whole sky, so we see the ones even in pretty wacko orbits. And what we do is we know the performance of our sensor. We know how well it works because we can look at lots and lots of reference stars and build up a pretty good model of what we should have been able to see. And then we basically kind of say, okay, well, let's create a synthetic model population of asteroids. And then we kind of play that through our simulated survey, and we tune it until it matches what we actually saw. And in that way, we can kind of back out the sample that we saw. It's kind of like when you take a survey, you know, if you're trying to figure out, I don't know, political candidates or something, how people are going to vote. You try to poll a representative sample, and then you extrapolate to the larger population.
Yeah, Nielsen ratings. Or
yeah, Nielsen ratings, exactly. It's the same thing. Everybody has a little box, and you know, you try to figure out from that small group of people with the boxes, okay, how is everybody going to behave? So what we've done is we basically said, all right, this is what we saw. We saw this many objects. We should have seen this many, so that means the population really is this many. And that extends to the large ones as well. And one of the other things you have as a tool is as you keep discovering objects, you know which ones you found before. Well, if you keep catching the same fish, the exact same one, then you say, okay, we already saw this one, throw it back. Okay, let's try again. What else do we see? Oh, saw that one already. And it gets to a point where you stop finding new objects. You just keep finding the same thing over and over and over again. Now, there's two possible explanations. It could be that you found them all, or it could be that maybe there's a whole group of them that you just can't see for some reason. To eliminate the latter possibility, that's where we use our understanding of the model populations and our sensors' sensitivity to figure out, yeah, we really did cover the whole phase space. If there was something there, we would have seen it. Right. So we know for the big ones, we are, like Don said, we're more than 90% what we call complete now. We found more than 90% of the really big stuff. That's the good news.
Yeah.
So,
and those are the easier ones to spot, I would imagine, just because of their size and potential composition.
yeah.
Oh yeah, they're much easier to find because they're larger of course.
Yeah, we can see them in greater distances.
I know we have this chart of known near-Earth asteroids, and this kind of blew me away. I don't know if we can get it up on the Hangout, but basically it's the large ones. There it is. The large ones, don't grow that much, but the total number just skyrockets. Is that because of the equipment's gotten better? There's more people looking. What's the reason for that?
Well, the interesting part of this graph is around 1998, NASA got serious about looking for near-Earth objects, and you can see it took off at that point. The red curve, as you pointed out, represents the 1 kilometer and larger sized objects, and we've almost discovered that entire population, about 95% of it. So the curve is pretty level. We're not finding a whole lot of those new ones. On the other hand, the small ones, smaller than a kilometer in diameter, there's so many more of those, and we haven't discovered nearly as many, so we're still finding more and more as the technology and the techniques improve.
It's also worth pointing out that, the old video game Asteroids, I mean, that game actually, that was a great game. I spent way too much time when I was a kid blasting Asteroids.
I did.
But, that was actually a pretty good game in the sense that it was actually somewhat representative of how the real asteroids work. A bigger one collides with something and breaks into many smaller pieces. And so there are always lots more small pieces than there are big ones. We call that the size-frequency distribution. That's the wonderful jargon term for it. But it turns out the game was actually about right. Lots of small pieces.
Maybe we should rename it the Asteroid Game Effect or something.
Yeah. Why not?
I think it's probably, Asteroids is a more catchy name than size-frequency distribution.
Yeah, size-frequency distribution is kind of boring.
So, you mentioned earlier, Amy, that one of these larger asteroids is going to get within radar range, and you said 3 lunar distances, I think?
Yeah, roughly three or so times the distance of the Earth to the Moon, yeah.
How often does one get close enough that it's in between us and the Moon? I know that we had one recently, and it seems like they happen occasionally. So how often is this?
Well, we know that 2012 DA14 actually did just that, and the year is 2012 that happened. That's part of the name. So yeah, it does happen reasonably often, but these are usually very tiny objects. And of course, as Don pointed out just a second ago, the more you look, the more you tend to find. So these things probably do happen, but they tend to be very small. As our techniques get better, and as we have better observers and better instrumentation, then we're going to find more. So that's also part of it. So I think these things probably happen fairly often, but they're very small.
I worked this out just about a couple hours ago, and for the 7-meter-sized objects that Brian is interested in bagging and bringing back to the lunar orbit, you would expect an object of that size to actually smack the Earth every 30 years or so, and you'd expect an object of that size to pass within the lunar distance, the distance to the Moon, every 3 days. So these objects are very plentiful. There's millions of them. Yeah.
3 days?
3 days.
Wow. Jeez.
Most of the time we don't see them.
Yeah, almost all of them. Yeah, we don't see them. That's right.
And that's why, so NASA is considering ways to upgrade the systems so that we can see more. There are space-based methods to do that. There are ground-based methods. In practice, you probably need a combination of both types of systems to really, cover the phase space a lot better.
Right. Right. Yeah. In fact, there's an ATLAS system that's under development by folks at the University of Hawaii. It's several small telescopes that are designed not to find these objects well in advance of an impact, but to find them on their last so-called plunge to Earth and give the affected areas a couple of weeks of notice so that you can just evacuate the city if necessary, or get away from the water's edge if there's a tsunami.
Man, this sounds like a job for Bruce Willis.
Yeah, oh yeah. Not Bruce, no.
We've done some talking in the past about that movie. I think every asteroid scientist.
Fantastic movie.
God, that movie in their sights. I'm pretty sure.
I actually have never seen it. I've never seen it.
Shame on
Oh, wow.
Never saw it.
I feel like we're going to have a movie night, you guys.
Yeah, oh yeah.
Movie night.
Okay. Sounds good.
Watch that and Deep Impact. It's going to be a good night.
Double header.
When it comes to the close ones, those, in my mind, that seems like the one that like Brian would want to go out and grab. I feel like if you know it's going to pass by, are the ones that you're looking at, Brian, going to come close to us or what?
Yeah, they need to come close to us, and they need to be coming by relatively slowly, about a relative velocity of about 1.5 kilometers per second. So that's the kind of gravity effect, change in velocity the moon's gravity can give us. So we're looking for relatively small and relatively slow-moving bodies going through near the Earth-Moon system. So a few lunar radii, a few distances between the Earth and the Moon is kind of an ideal target.
Cool. How would you get to something like that? I mean, you use a chemical rocket, likely you get it into orbit.
No, this is the key. The key to the whole asteroid redirect mission is the technology of solar electric propulsion. That's where you take the energy from the sun, you collect it on very large solar arrays, and then you use it to accelerate, in our case, xenon ions to very high velocity. And that allows us to fly out and rendezvous with these relatively fast-moving objects relative to in the solar system, and then rendezvous, and then spend time with them, and then apply the thrust of those engines to change the velocity just enough such that they'll fly close enough by the moon that the lunar gravity can slingshot them into a lunar orbit. That solar electric propulsion, we're advancing the state of the art. We're going to 50 kilowatt class systems, ion engines that are accelerating ions to 30,000 kilometers a second, way beyond the technology that we used on the Dawn mission. Another interesting thing about ARM is we need a lot of propellant. We're able to carry as much as 10 tons of xenon. If you look at Dawn carried about 500 kilograms. So this is a whole new class of a solar electric propulsion system, which also has a lot of application for other things, for science and particularly for human exploration.
Very cool. We've got a cool video of that somewhere. We'll have to see if we can throw it up there.
Yeah, we've got a video of the ion drive, right?
There's an ion drive engine out there.
Here we go.
Oh, look at that.
That's
cool.
That's an engine
What thrust is that?
running. Yeah, those engines only put out, about less than half a newton of force, so it's a very light force, but they thrust for long periods of time, for years, and it builds up very large changes in velocity very efficiently. To do what we're trying to do with a chemical propulsion system would take 10 to 100 times as much propellant as what we're carrying.
And this isn't science. This is technology that's actually in use today, isn't it? I mean, there's space missions that are currently using ion drives.
Oh, absolutely. Yeah, with the Dawn mission, of course, depends on that. Commercial satellites use small ion engines for attitude control and for station keeping. But yeah, where we want to go with ion drive, though, is that if it's really a key part of the human exploration program. NASA's about sending humans to Mars. And to do that, we're going to need to deliver a lot of hardware and propellants to Mars. And a very efficient way to do that is using these solar electric propulsion systems. So we'll take our 50 kilowatt system and scale it up to 100, maybe 300 kilowatts, and deliver sizable payloads very efficiently to the Martian system. But on the way, we want to prove ourselves, using the moon as a proving ground. And that's why ARM is currently targeted to bring an asteroid back to cislunar space and put it in lunar orbit.
Yeah, one question I had was related to the, I don't know if JPL is covering this, but of course with our atmosphere on Earth, we've got a protective sheet around us basically that helps burn up a majority of small asteroids. With the moon, I mean, we're always talking about lunar colonies and whatnot, but there's no atmosphere on the moon. How often does the moon get hit? Because we're talking about rocks that are coming towards the moon and the Earth, and how often does the surface of the moon get hit? It's just a random question for anybody if you actually know the answer, because I don't want to be one of those colonists who ends up getting hit by a flying space rock.
Well, the moon gets hit less frequently than the Earth because the Earth is so much more massive, of course.
Sure.
But you're right. The moon has no atmosphere for protection. But these are rare events. So either you could build habitats that are in caves, or you could probably take your chances and build habitats on the surface and not really worry about a serious impact on your abode.
And there actually are astronomers who are monitoring the moon. There's a network of people who do this, and it's the lunar flashes that they look for. They basically look for little bright spots appearing on the moon. It's actually a very useful scientific technique for trying to understand how many of these smaller little impactors there are, really little things. I mean, we're not talking about really big stuff by and large, because this is happening fairly often. But it's a good way to kind of help to nail down how many tiny pieces of space rocks are out there that come into the Earth-Moon system.
Yeah, that's Bill Cook at Marshall Space Flight Center is doing a lot of that work and doing it well.
Cool. Cool. Wow. And just to go back real quick, if I remember from my middle school physics, when you said it's a half a newton is like the weight of a nickel. So that's very light. That was what my science teacher told me. It was the weight of a nickel is like 1 newton.
Okay. All right.
So that's pretty light force. Well, I mean, it have to burn for a long time, I imagine.
It does. It does. But it accumulates velocity very effectively. Keep in mind that those ions are coming out at very, very high speed, 30,000 meters per second. So they're moving really fast.
That's pretty cool. Wow. So we're watching the moon for hits. We're watching the skies as best we can. Sounds like we've got it pretty covered, but we don't really, right?
Yeah, we still have a lot more left to do. I mean, that plot that you saw, the graph with the red line, flattening out, that's the good news. The other part of it is we still have a lot more work to do, because that blue curve just keeps going up and up and up and up. We estimate from our NEOWISE survey that about 25% of near-Earth asteroids that are larger than about 100 meters across have already been found to date. So that leaves about 75% more in the 100-meter size range that we still have to go out and find where they are. And then, of course, as Don mentioned, for smaller objects, things that are smaller than 100 meters, we have a lot more left to do on those. And there are probably millions of them down to Chelyabinsk size. So that leaves the door open for a lot more astronomy to be done to find these things. But the good news is we have some ideas on the table that we've been working on to try to do that, to improve the situation. So
yeah, there's all of the surveys are improving their systems, improving their instruments on an annual basis, so that that blue curve just keeps rising, and the number of discoveries provided mostly by NASA-supported facilities just keeps rising. But even so, there's so many of them that we have job security.
Yeah, I guess so.
That's great. that's very helpful.
So one of the things,
Taylor, I'm sorry, I was.
Oh, go ahead.
Oh, I was going to say Taylor Hauser has a question in the Q&A area, and he wanted, it may be a she actually, Taylor could be there. Taylor wanted to know, what are your recommendations for someone who's looking to get into the space industry? So maybe somebody who wants to help out spotting the asteroids.
Well, math, physics, and neglect not your writing classes. Those are actually pretty important too. Everybody thinks that if you're just studying the science subjects that you don't have to pay attention to any of your humanities classes, but we work in big groups, and we're always having to talk to lots of people, including you guys, and so being able to read and write and talk about what we're doing is also very important. I think the main thing though is just engage your curiosity and stay in school to study physics and math if you can. That's a really good starting point. And then when I don't know what level the questioner is at in terms of their education, but basically engineering degrees, physics degrees, those are all really good entry points into it. And just stay curious. I think that's the main thing.
Actually, NASA has something called an Asteroid Initiative underway, whereby the public is being asked to provide ideas for discovering these objects, for deflecting these objects, and there's been an incredible response. And we're hoping that once we wade through all of these responses and suggestions, that we'll find a couple of gems.
One other thing, too, that was worth pointing out for any students who are listening, NASA has internships. And one of the best ways, if you want to get your hands dirty and see whether or not you like this space stuff, it's one thing to, watch sci-fi, but it's quite another to be, here on the ground doing kind of the dirty work. And so to see if it's for you, try out a NASA internship. The websites have some links to them, and we've had some wonderful students come through our group. It's been a lot of fun.
How could you not like space stuff? I mean, really.
I know, right? I went to space camp when I was 11, and I was hooked ever since. That was all it took. I mean, I was already excited, but it was awesome. It was so fun. And what we definitely wanted to get to, because I know how much Ian loves meteor showers, and I cannot pronounce this one to save my life. Camelopardalis?
Let me have a go. Is Camelopardalis?
Not even close.
But they said there could be either be 1,000 shooting stars an hour, or 1,000 atmospheric impacts, or maybe none. Why don't we know?
Well, all right. So these Camelopardalids, that's the only time I'm going to try and pronounce that, will be emanating out of the constellation of Camelopardalis, which is a very faint constellation. Never mind Camelopardalis. Just look for the Big Dipper and the North Star, and these meteor showers should be emanating from that region Friday night, about 11 o'clock or midnight Pacific Daylight Time. So this comet, which is called 2009 P Linear, has been around the sun many, many times, and several modelers have thrown off on their computer models bits of gas and dust every time the comet comes back to its closest approach to the sun. Then they ask the question, how do these clouds of dust evolve with time? And many of the modelers have come to the conclusion that a lot of these clouds of dust will congregate right on the Earth's path on May 24th, which is Friday night, and the Earth will just run through them, and we'll get anything from maybe 20, 50, 100 meteors per hour as a result. We may not, but I think the chances are pretty good, so it's worth a look. Just go outside, get your eyes dark adapted, look up, and about midnight on the west coast, and you should see something, hopefully.
Wow.
Yeah, that's the best thing about that's why Trace said that I like meteors, because I don't have a telescope. I mean, how sad is that I don't have a telescope? But the best thing about meteor spotting is you can go out in the backyard and just lie back and just watch. And the good thing is we kind of got an open backyard, and even though I'm based in LA, there is a bit of glow from Los Angeles. Generally, we're blessed with fairly clear skies, and some of the brighter ones you can see. And it just makes for a nice evening. I mean, go outside with some warm clothing. Even during the summer, it can get a little bit cold if you lie on your back for too long. And just look up. I mean, that's the best bit of advice I was given, and that's all I ever do. It's the most lazy form of astronomy. And I love it.
It's one of Mother Nature's best light shows.
Yep.
Absolutely.
Forecast calls for meteor showers. So.
Yeah.
Looking forward to it.
Well, we'll be in our hot tub looking, Don.
Okay. Spoken like a true engineer.
Well, let's see if we can't get through a couple more of these questions. Brian, what is the benefit directly for sending a mission to capture an asteroid? What can people find out from just from capturing?
Well, the primary benefit of this whole mission is to demonstrate the technology of the solar electric propulsion to advance that, and then return to the lunar system where we can send crew. So this is really the first time humans will have been out at the moon since Apollo, and our mission will actually have EVA out at that condition. So we'll be demonstrating for the first time since the Apollo era the capabilities that we're going to need to go beyond the Earth, go beyond the Moon, and make our way toward Mars. So we're considering this as part of a proving ground of activities, and ARM being a central part of that. So that's the primary, fundamental objective. Now, relative to the asteroid, of course, from my point of view, not being a scientist, I'm very excited about actually seeing an asteroid up close and understanding something about the structure. What's underneath the surface? How is this a rubble pile? How is it held together? Is it a lot of little pieces? Is it a group of big pieces? We see the surface with our observations, but we don't really know what's underneath, except when we see coming through the meteoroids as they hit the Earth. So I'm really excited about understanding how asteroids are really held together.
Yeah.
I suppose in connection with finding out what these asteroids are made of, there's a question here from Yusuf Manzi, and he's basically asking, it's moved. But basically the gist of the question was, with the asteroid mining companies that are emerging, like Planetary Resources, how close are we to developing these technologies? I mean, can we actually refine this stuff in space? Is there any known techniques that we can use to do that? And what kind of money are we going to be making here if it's actually going to, I mean, Don mentioned that there's no real business plan here yet. We don't really know what they're made of. So why is there this massive interest that private companies, I mean, you've got the likes of Google founders that are jumping on board and all these entrepreneurs that want to make some cash in space. But I would argue that you're not really making any money in space, you're just developing technologies down here on Earth and making an industry down here. Basically, the gist is, are we actually even close to mining gold on asteroids? That's what I think.
In my opinion, no, I don't think we are close to that. I mean, I think what ARM can do is bring back asteroid material that you could relatively easily send out these in situ resource utilization experiments, where you can actually take some of that material and try to demonstrate how you would process it. Of course, the first thing you do is you bring back, one of the beautiful things about the redirect missions, we, with the crew, can bring back kilograms, large quantities of this material, and then here in the laboratories on Earth, evaluate it. What is the composition? What could we mine from that? How much of what materials are there? But as I said earlier, the C-type, the carbonaceous chondrite, and ideally with water, as Don mentioned earlier, is really what you'd like to have for resource utilization. The most obvious one, from my point of view, is water for propellant. And so for that, you've got to get a C-type or go to a C-type. So I think the business model is still very uncertain for resource utilization. And we'll just have to see what, like I said, we're helping that process along if we bring back the right kind of asteroid.
One thing that's worth pointing out is that, most of the near-Earth objects have fairly wacky orbits in some sense. They tend to make close approaches sometimes, but they have high inclinations, meaning their orbital plane is tilted pretty high with respect to the plane of the solar system. And they can have fairly eccentric orbits, meaning kind of squashy shaped. That means that while they might make a close approach, they'll do so at a pretty high speed. So what we're interested in, especially when we look for things that represent a potential collisional hazard, are objects that have a chance of getting close to the Earth and then make frequent close approaches after that too. Those are the really interesting objects. So in some sense, if something is close enough to be interesting for some of those guys, we certainly want to pay attention to it from a collision standpoint.
Yeah, that's a great point Amy makes, is that the same objects that are easiest to get to via spacecraft are also the same objects that represent the biggest threat to Earth, so they're doubly interesting.
Yes.
Yeah, for sure. Can you just describe, a Treknologist wants to know what a wacko orbit is.
I'd like to know that too.
What's a wacko orbit?
I think a lot of people think about
calls you too often or something.
Yeah, that's it. It's a really strange orbit.
It's a technical term.
Yeah, it's a very technical term. Yeah, so basically the near-Earth objects, they do tend to have a higher dispersion of inclinations than we see, for example, among the main belt asteroids. And that has to do with how the near-Earth objects are delivered into the region near Earth. I mean, most of the asteroids in our solar system are safely between Mars and Jupiter, and they stay there for, they've been there for billions of years. They're probably going to stay there for just as long. Occasionally, however, some of them leak out and get into the inner part of the solar system, and they usually do so via interactions with the other planets gravitationally. So kind of the slingshot effect, if you will. And that has the effect of kind of scrambling the orbits up a little bit and giving them higher inclinations on average than the main belters tend to have. So
got it.
That's why.
So they become wacko.
Yeah.
Okay, I think we have time for one more question, so I figure we'll make it a big one. What would be, according Sean Thompson and Mateo Chio are asking about what would be the plan if we found an asteroid that was aimed toward us? If we were in the sights.
Well, that's a good question. Maybe we could toss up the deep impact still. The easiest and cheapest and most demonstrated technique would simply to run into the asteroid that was predicted to hit the Earth with a spacecraft. Slow it down a millimeter per second or two so that in 10 or 20 years when it was predicted to hit the Earth, it would miss by a wide margin. And this is a still from the Deep Impact mission where we purposely ran a spacecraft into Comet Tempel 1. And we're showing this to demonstrate that we have the technology to navigate a spacecraft, to zero in on the target, and to hit it. And so that navigation technology has already been demonstrated. So the easiest technique by far, to my way of thinking, is to run into it with a spacecraft. And if you have time, you could send another spacecraft to orbit the asteroid and determine the orbit before and after the impact. And if you didn't quite do enough with your initial impact, you could use the SEP spacecraft that you've already sent there to either employ a gravity tractor that would use the gravitational attraction between the asteroid and the spacecraft to move it just a little bit, or you could use the ion beam of the solar electric propulsion to actually impinge the asteroid and move it just a tiny bit that way. So that would provide so-called trim maneuvers to the initial impact.
But at what point do you deliver the nuclear weapon? That's what I want to know. When does this happen? At what point in the mission does that blow up?
Yeah. When do we deploy Bruce Willis?
That's what we need.
Well, if you don't have enough time to do it with a impacting spacecraft or a gravity tractor or an ion beam impingement, there is the option of using nuclear explosives. You could set them off the surface and use the neutron flux to ablate the front side material and introduce a thrust, or you could try and bury the explosion in the asteroid in hopes of fragmenting it into pieces small enough that they wouldn't get through the Earth's atmosphere. So that's an option of last resort.
But the trick is we really want to find them early.
Yeah.
That makes a big difference.
That's right. One of the things we're going to do with the asteroid redirect mission is actually demonstrate some of the techniques that Don talked about, the ion beam, deflection, and the gravity tractor. So we'll actually be able to show the world we know how to do those sort of things.
Wow, so we're already working on this. That's pretty cool. That's great. Well, I think we've wasted another hour, guys. This was awesome. This was so much fun. There are a lot more questions that we didn't get to, and I apologize to those people. Thank you for asking your questions. You can still tweet on the hashtag #SpaceOut. I know we at DNews will be monitoring it. Ian probably will be. And I'm sure somebody over at JPL will be looking at it too, so maybe we'll be able to answer some more of your questions. Thanks a lot, guys, for coming and joining us talking about asteroids today.
No problem.
That's fun.
All right, thanks, Ian, and everybody have a great day and keep looking up.
Cheers, guys.
Bye.
Bye-bye.